Let's dive right into this explainer. Today, we're unpacking the fascinating evolution of search algorithms. We're going to trace exactly how computers retrieve information, starting from the old-school keyword matching we all grew up with, all the way to the cutting-edge mathematical fusions that are literally transforming how enterprises handle their data today. If you've ever wondered how modern AI systems actually decide what information is relevant to you, well, you're absolutely in the right place.
To really grasp why this evolution is absolutely crucial, wrap your head around this staggering number from the Baymart Institute, 31%. That's the percentage of e-commerce product searches that come back with 0 results. And the kicker? They fail even when the exact item the customer is looking for actually exists in the catalog. Think about that. For users who typically convert at 2 to 3 times the rate of casual browsers, a 0 results page isn't just an annoyance, it's a massive direct revenue leak.
So, let's jump into our first section, the AI search dilemma, where we tackle the lexical gap versus attribute blur.
That massive 31% failure rate brings us to a fundamental hurdle. For decades now, we've relied heavily on an algorithm called BM25. It's powered search engines since the 90s, and it's still the default in massive systems like Elasticsearch. And honestly, there's a very good reason for that. BM25 is an incredibly fast, deterministic industry standard. It's an absolute powerhouse when it comes to matching exact SKUs, part numbers, and specific model identifiers, all with sub-millisecond latency.
But it has a fatal flaw, which engineers call the lexical gap. Because BM25 relies entirely on exact character matching, a very strict, literal approach, it completely misses human intent. For example, if someone searches for a pregnancy dress, they might get 0 results simply because the catalog used the term maternity gown. The system has no clue that a respirator mask and a face mask are related, or that a lined parka is literally exactly what you want when you type in warm winter jacket.
So to fix this lexical gap, engineers brought in dense AI embeddings. These vector searches actually understand broad concepts and connect those synonyms beautifully. Problem solved, right? Well, actually scratch that, because this introduces a brand new headache called attribute blur. Because dense models prioritize overarching meaning, the AI might confusingly recommend a 128GB iPhone when you specifically searched for a 256GB model. To the AI, the semantic meaning of those two phones is nearly identical, so it just blurs right past the exact technical specs you actually needed.
Which brings us to Section 2, the hybrid search solution, trying to get the best of both worlds.
Search engineers quickly realized they shouldn't have to choose between exact keywords and broad concepts, so they built hybrid search architectures. By running both systems in parallel, you capture the exact precision of keywords, meaning you get that 256GB requirement, while also catching the broad recall of semantics, so you don't miss the maternity gown. It's brilliant, but now you've generated 2 completely distinct ranking lists with totally incompatible scoring systems. Seriously, how do you mathematically combine a BM25 keyword score of 12.4 with a dense vector similarity score of 0.85? It's like comparing apples to airplanes.
Let's move to Section 3, fusing ranks with RRF, and how we ignore scores to find consensus.
To act as a peacemaker between these incompatible lists, data scientists turn to reciprocal rank fusion, or RFF. RFF operates on a brilliantly simple premise. If we can't fairly compare the raw mathematical scores, let's just throw them out entirely. Instead of trying to somehow normalize a keyword score with a vector score, RFF focuses purely on the document's rank position. The logic is that documents showing up at the top of multiple different lists are just likely the most relevant overall.
You can see exactly how this works with this MongoDB example for a Paris sightseeing search. Notice how the Eiffel Tower rockets to the absolute top of the final list. Why? Because it literally aggregates points by ranking highly on both the keyword and the semantic lists. It wins by sheer consensus. Meanwhile, Montmartre, which ranked number 1 semantically but didn't even register on the keyword list, gets pushed way down. RGRF intensely rewards agreement. Now, this magical math relies on a specific smoothing constant, which is typically set to 60. By adding 60 to the rank position in its formula, RRF prevents any single overperforming retriever from completely dominating the results. It flattens the curve just enough to force the system to prioritize agreement across all engines. Basically, a result loved by both systems will always beat a result loved by only one. But, as we'll see in Section 4, the limits of RRF. Sometimes, rank just isn't enough.
Look, RRF is a massive leap forward, and it's a default in popular tools like LangChain4j. But we really have to pause and ask ourselves a critical question. By throwing away the actual mathematical scores and relying only on rank positions, are we leaving incredibly valuable relevance data on the table? Think about it. If one document is a 99% semantic match and the next document down is only a 40% match, RRF just sees them as rank 1 and rank 2. It completely ignores that massive 59% cliff drop in quality.
Recent research from NewMind AI really highlights these exact blind spots. Because of RRF's rank-only focus, it fails to reflect the massive magnitude of differences between an amazing hit and just a mediocre one. Plus, that fixed k equals 60 parameter, it doesn't adapt well to different result distributions. Worse still, RRF blindly treats every single data source as equally trustworthy. This means it is highly vulnerable to irrelevant outputs. A terrible result from a poorly tuned subsystem can still drag down the final ranking just by showing up on a list.
So how do we fix that? Section 5, Next Level Score Fusion, introducing DBSF. To solve those glaring blind spots, data scientists needed a way to safely translate wildly different raw scores. And this is where distribution-based score fusion, or DBSF, totally changes the game. DBSF acts as a universal statistical translator for heterogeneous search methods. So instead of throwing the scores away like RRF does, DBSF keeps them, but it forces them all to play by the exact same mathematical rules. Let's break down this process step by step, because it really is brilliantly logical. First, DBSF calculates the mathematical average, the mean, and the standard deviation of a single system's results. Second, it chops off the extreme outliers, clamping anything beyond 3 standard deviations so those crazy anomalous spikes don't ruin the math for everything else. Third, it converts these adjusted scores into a common, clean 0 to 1 scale. Finally, now that everything is speaking the exact same language, it just cleanly adds them across all the different retrieval methods. What is so cool about this is that this scaling creates a statistical safe zone. It completely prevents a model with a huge numerical range from bullying a model with a smaller range. If your keyword scores go from 0 to 100, but your vector scores only go from 0 to 1, DBSF completely neutralizes that scale difference. But, and this is key, it perfectly preserves the actual magnitude of relevance within each list. It's just fundamentally fairer.
And hey, the proof is right there in the benchmarks. On rigorous tests like the Beers SciFact dataset, DBFs consistently outperforms RRF. It scores significantly higher on precision because it respects each model's relative confidence rather than just settling for a rank-based popularity contest. It basically proves that keeping score magnitude data, when you normalize it correctly, leads to noticeably better search results.
So what does the ultimate Goldilocks pipeline actually look like for an enterprise AI agent today? First, you retrieve your top candidates using hybrid search, getting both exact keywords and dense semantic concepts. Second, you mathematically normalize those raw scores using DBSF. Third, you can actually layer RRF on top of that to guarantee rank agreement. And finally, you take that perfectly fused, consensus-driven list and pass the very top candidates to a deep learning cross-encoder for absolute pinpoint precision re-ranking before serving it up to the user.
The folks at NewMind AI hit the nail on the head here. Relying on a single ranking method is entirely obsolete. Modern systems demand dynamic, mathematically sound fusions. You just can't rely only on keywords anymore, and you absolutely cannot blindly trust vector embeddings. You have to weave them together intelligently.
I want to leave you with this provocative thought to consider about your own data architecture. If 31% of searches are failing, how much revenue or how many critical, game-changing insights is your current system hiding right now behind the lexical gap? And more importantly, how are you going to use tools like RARF and DBSF to finally reveal it? Hopefully, this explainer gave you the exact blueprint to start fixing it. Thanks so much for learning with us today.